Here's a tutorial on Unit 5, Section 4.1, Exponential Functions. The equation for an exponential function reads f of x equals a times b to the x minus h power plus k. We know that f of x is the y variable and x is the x variable. A is the leading coefficient. In the problems we'll work with, a will always be plus or minus 1. B is the base, h is the horizontal shift, k is the vertical shift, and y equals k is the equation for the asymptote, and we will discuss asymptotes in just a moment. The topics we're going to cover are understand the number e, calculate exponential values, graph exponential functions, graph and write an equation for the asymptote, find domain and range of an exponential function, and solve exponential word problems. Let's begin with the number e. Perhaps you know that the two subsets under real numbers are the rational and the irrational numbers. Rational numbers represent terminating or repeating decimals. The irrational numbers are non-terminating and non-repeating decimals. E falls in this category. You may be familiar with other irrational numbers such as pi or the square root of 2. All of these numbers can never be written down in decimal form. We can only write down a decimal approximation, as you see here with the number e. The number e was named for the Swiss mathematician Leonhard Euler, who lived in 1707 to 1783. He used the number extensively. However, John Napier used e for the first time in 1614. It is the base for all natural logarithmic functions. To find e on the calculator, there are two ways. You can either click on Shift Natural Log, that is the more common way, or you can also click on alpha, and then you see here the key at the bottom, times 10 to the x power. Now we will calculate some exponential values using the Casio calculator. 2 to the 5.3 is approximately 39.397. You're rounding to the thousandths place value. 3 raised to the square root of 2 is approximately 4.729. And e to the negative 1.4 is approximately 0.247. I'll demonstrate the last one using the calculator. So I will begin with clicking on Shift Natural Log, and you see a box is provided for the exponent. So I'll enter the exponent negative 1.4 and press equal. Here is a decimal estimate to which we round the third place value, namely 6 thousandths. It rounds up to 7 thousandths. Now let's look at a graph of an exponential function and its asymptote. What is an asymptote? An asymptote is a broken line to which the given function moves infinitely closer. The graph never intersects the asymptote. Here are some examples. What you see here in the blue graph is the parent graph y equals e to the x. It's not enough to just graph the equation itself. You must also include the asymptote, which happens to be y equals 0, which coincides with the x-axis. In the next section of this unit, we will work with logarithmic functions. Here we see the parent graph of a natural logarithmic function, and this time the asymptote is the vertical line x equals 0. Here are some examples of various parent graphs for exponential functions. You can see the different bases. Here we have base 2, now base e, base 3, and base 5. And as the base increases in value, you see that the graph rises more quickly. A pattern to notice among any exponential parent graph is that every single one of them cross the y-axis at 0, 1. Another thing they have in common is that they all have the same horizontal asymptote, which has the equation y equals 0. Let's graph y equals, or f of x equals 2 to the x using points to plot. If you run -2 through the calculator, or you can do it by hand as well, in other words, you're raising 2 to the -2 power and expressing it in fraction form, you'll get the fraction 1/4. Enter -1, we get the fraction 1/2. Enter a 0, a 1, and a 2. Now plot these points and you'll have an approximate graph of y equals 2 to the x power. In addition to that, you do have to write and graph the asymptote. So the asymptote is based on the constant k at the end of the equation, which in this case is 0. So the equation for the asymptote is y equals 0, and we graph the broken line. Here's another example, very similar, and we're going to compare it to the previous graph, which you see there is a small sample of it up here in the upper right corner. This time, the exponent has a negative in front of the x. So running these values, same values, through the calculator, you'll see we actually get the same y values except in reverse order. So how does that change the graph? It actually describes a graph that could be called exponential decay. It's declining in value as we view it left to right. Here is the asymptote, as usual, y equals 0. And so what pattern can we describe that takes place between the original parent graph 2 to the x and what is now 2 to the negative x? Do you see that the minus sign in front of the x causes the graph to reflect over the y-axis? Now we have a negative in front as a leading coefficient. What happens to this graph as we compare it to the original parent graph, y equals 2 to the x? Run the given values through the equation, plot them, and how would we describe this? Let's compare it for just a minute to this original function. How did we get from here to here? What happened? What is the meaning of this minus sign in front of the 2? You probably already know from other graphing other functions. Let's first get the asymptote, of course, y equals 0, and graph it. Now we'll answer the question, what is the meaning of this minus sign out here? Do you see, and as you probably already know, it causes the graph to reflect over the x-axis. The original parent graph reflects over the x-axis. To find points on, if you'd like to just find some points on the Casio calculator, the steps would be to begin at mode 7 and type in the given function. Perhaps your function looks as complicated as this one here. And understand that if you do ever want to type a variable within mode 7, you click on alpha and then the closed parentheses key. So always remember to press equal after each particular step. So first you begin by typing in the given function and press equal. This will move you to the g of x screen. This is something we just skip. We don't have a second function. Then the next screen will be labeled start. A suggestion is to start with a small number like -5. Then the next screen will say end, perhaps at +5. And the next screen will say, what is your step? I recommend always letting the step equal 1. There are rare exceptions to that. And then by clicking equal for the last time, you'll be able to view the chart of points. I will demonstrate this in one of our equations in our tutorial. All right, so here is f of x equals 5 to the x plus 2. We're asked to graph using transformations. So we begin with the parent graph y equals f of x. The horizontal shift, as you know, will be -2. Why is that? Because here we see x plus 2, and we know to write the opposite, -2. That means this significant point, it's no longer at the origin. The significant point is now 0, 1. And we shift it to the left 2 units. The asymptote will be, of course, the constant at the end, so it continues to be y equals 0. But how about this equation? We begin with the parent graph y equals 5 to the x. There is no horizontal shift, but there is a vertical shift. The vertical shift is -3. So counting down from the significant point 0, 1, counting down 3 units, we end at 0, -2. Also, graph the asymptote. Notice this time it will be a little bit different because the constant at the end now is -3. So the equation for the asymptote is y equals -3. And here is the graph of it. Now we have all the parts. We begin with the parent graph, y equals 2 to the x. The horizontal shift is 3. It's the opposite of -3. The vertical shift is -4. So we start at the y-intercept 0, 1. We move to the right 3 units and down 4 units. Now we graph the asymptote, which of course has the equation y equals -4. If we did want a few points to plot here, other than the one we can arrive at using transformations, here is how to type this into the calculator. Click on Mode 7 and type in 2. Click on the raise button, X to the box. The variable, as you know, is alpha, close parentheses, then -3. Now, to get the cursor back down on the ground, we have to click the side arrow and then type -4. Always look back at what you have typed and make sure it reads the way that you want it to. So we've typed in the given function and we press equal. As you can see, we have this g of x function. We can just skip over it. So press equal again. Where do we want to start? Well, looking at this graph, perhaps I would want my values to begin at a -2 and maybe go to a +7. So here I'll start at -2 and press equal, and end at 7 and press equal. As you can see, the step is 1. That's how we should leave it. So press equal. And here is our chart. I'll scroll down until I find some friendly points, ones that might have at least something I could graph. So I see here that the point 2 and -3.5 would not be too difficult. If all you had were rather complicated decimals, I would recommend just rounding any particular decimal to the tenths place value and graphing it that way. But I'll continue to scroll down. And of course, I already know about 3 and -3, but perhaps I want one other one to the right. Here's an excellent point, 4 and -2. That would just make for a better graph. Here's another point, 5 and 0, 6 and 4, and, well, this one is too large for the graph, the 7 and the 12. But if you did plot a few of those, it would make for a better picture. All right, so let's graph this parent graph, 1/3 raised to the x, as well as the given function. So we'll start with the parent graph. This is what it looks like. Again, if you would prefer to have a few extra points, just type this into your calculator under mode 7. The horizontal shift, as we look at the graph here circled in green, we can see it is +2. It is the opposite of -2. And then the vertical shift is 5. So going from the significant point 0, 1, we shift to the right 2 units and up 5 units. And we end at 2, 6. Of course, we still have to graph the asymptote. What would be the equation? It would be y equals 5. So here is the graph of it. In one of your problems, you'll be asked to graph all of these functions on the same Cartesian plane. So here is a parent graph, f of x equals e to the x. But if we are graphing g of x equals negative e to the x, we know the negative in front of the base, in other words, the leading coefficient is -1. That simply causes the graph to reflect over the x-axis. We know this, that it flips the graph down. We had prior experience using graphing parabolas, where if the negative was out in front, it just made the parabola turn downward. So the same thing here. The exponential function is simply going to flip down, and it reflects over the x-axis. Now notice this last one has both. It has both the negative in front and the negative in front of the exponent. So what this does is two things. It flips it down, like you see the green graph, and then it also flips it or reflects it over the y-axis. So here is the final result of that. So you'd have to imagine the green reflecting over the y-axis to get the final answer here that you see in the red, the h of x function. Now let's talk about domain and range. The domain of any exponential function is very similar to the domain of a parabola. It will get infinitely wide. So the domain is negative infinity to positive infinity every single time. But as you know, the range is a matter of viewing the graph. We begin at the asymptote, but notice it does not include the asymptote because although it's a little difficult to illustrate here, in reality that blue graph truly never touches the asymptote or crosses it. So, but it gets infinitely closer to the broken line, although my picture is somewhat limited. So we begin there, but we begin with a parentheses. That's the difference between this kind of graph and, say, a parabola. So it never reaches -7, but it does travel. In our picture, we can see it travels to positive infinity. All right, what about this exponential function? We know the domain is all real numbers. The range, we will begin at negative infinity and end at the asymptote. The asymptote, as you know, has the equation y equals 2. So once again, we view from the bottom up, from negative infinity to positive 2, but both sides have parentheses. Just remember that. All right, and here's another example. The range, once again, it ends at the asymptote, for which we know the equation is y equals 3. So here is how we view the range. We begin at negative infinity and stop at 3, leaving it open at 3. Now let's look at some word problems or exponential applications. Money is compounded n number of times annually, and we use this formula. A equals P, parentheses, 1 plus R over N, close parentheses, raised to the n times T. A is the amount to which the investment grows. P is the initial amount of the investment, otherwise called the principal. R is the interest rate expressed as a decimal. N is the number of times the interest is compounded. And T is the time in years. So let's look at this problem. Find the accumulated value of an investment of $10,000 for 5 years at an interest rate of 5.5% if the money is compounded semi-annually. Semi-annually means it's compounded twice. So let's identify the given information. The principal is $10,000. The rate, 5.5%, expressed as a decimal, is decimal 0.55, or 55 thousandths. The number of times compounded is 2 for semi-annually. And the number of years, we're going to leave this money in the bank, is 5 years. So here are all the values, substituting in for the variables, P, R, N, and T, and you can simply type this directly into your calculator exactly the way you see it. And your answer will be $13,116.51. Here's a second problem. Find the accumulated value of an investment. Actually, what we have here is the same information. This time, the money is compounded quarterly. So that is the only difference. Typing this into the calculator, we get this answer, $13,140.67. So you can see the fact that it was compounded 2 more times, or twice as many times, the final amount is just ever so slightly larger. I'd like to demonstrate this on the calculator to make a point about how to use your calculator efficiently. So we'll go back to mode 1, or you could go to mode 2 either, and I will type in 10,000, then parentheses, 1 plus the fraction decimal 0.55 over 4, and arrow to the side, close parentheses, click on X to the box, and type in 4 times 5, or you could just call it 20. I will actually call it 4 times 5 because I want to show you how to edit that. And then simply press equal. And you can see our amount is $13,140, and rounding to the penny, it would be 67 cents. Now, let's say my next problem did say semi-annually, compounded semi-annually. I can click on this back arrow and simply backspace, and I can change. I'll click delete and change the 4 to a 2 and continue to back arrow until I'm here again at the 4, and I'll delete and click on 2 and then press equal, and you can see here is the amount to which it grew in the previous slide. So that's a way, if you have to answer this kind of question several times, to not have to retype the problem. All right, and here is our final word problem. This time the money is being compounded continuously. When it's compounded continuously, we use the number E. E is part of the formula. So, of course, A is the amount to which the investment grows, P is the principal or the initial amount of investment, R, as usual, is the rate as a decimal, and T is the time in years. So here is our word problem, very similar to the other two. The initial principal amount invested is $10,000. The rate is decimal 0.55. The time is 5 years. Here, substituting these values into the formula for compounded continuously, we run it through the calculator and we see, once again, this same amount in interest rate and time produce a slightly larger amount because it is compounded continuously. So practice using your calculator, and this ends our tutorial on section 4.1, exponential functions.